Hi everyone, today we are going to see what is Vapnik Chervonenkis dimension, or sometimes it is referred as VC dimension. Okay, Vapnik Chervonenkis dimension. So what is this Vapnik VC dimension? So let us say we have a data set containing endpoints. These endpoints can be labeled in 2 to the power n way, which is true. If you have a number of points, we can label it in 2 to the power n ways. So let us say if you have 3 points, we can label them in 2 to the power 3 ways, 8 ways, okay? As positive and negative, right? So you have done it in, if I have, let us say, 3 binary, if I ask you to write binary numbers from 0 to 7, so you will be having 8 variations. So if you can consider those 0 and 1 as negative and positive, so obviously there will be 8 ways, right? And then this is 2 to the power n. Therefore 2 to the power n different learning problems can be defined by n data points. If for any of these problems we can find a hypothesis h, small h belong to capital H, that separates the positive examples from the negative examples, then we say H, capital H, shatters endpoints, okay? Shatters, distinguished, okay? That is, any learning problem definable by n examples can be learned with no error. So that will be like a pure shattering of positive and negative examples with no error by a hypothesis drawn from H. The maximum number of points that can be shattered by H is called Vapnik Chervonenkis. VC dimensions of H is denoted by VCH and measures the capacity of H. So this is a very interesting concept which set the path for classification of positive and negative example. If we think from binary classification point of view, it sets the path for positive and negative example. So Vapnik Chervonenkis dimension or VC dimension. So this dimension, what it does, it can we'll say that if 2 to the power n different learning problem can be defined by n data points, if for any of these problems we can find a hypothesis, that means you have to find a way H belongs to capital H, small h belongs to capital H, that separates the positive example from the negative example, then we say that H shatters endpoints, okay? And this whole concept is called Vapnis Chervonenkis dimension of H and denoted as VCH, and measures the capacity of H. So as I was mentioning, it shatters the point. So in this figure we can see that an axis aligned rectangle can shatter 4 points, right? Let us say this is let's say this is red points. Anyway, these 2 points, if you can consider this whole or these 4 points, so this can be pairwise, it can be shattered by a rectangle, okay? By a rectangle. So an axis aligned rectangle can shatter. Axis aligned means it will be like this, it will be like this, or it will be like this, okay? Axis aligned rectangle. So the VCH, when H is hypothesis class of axis aligned rectangles in 2 dimensions, is 4. In calculating VC dimensions, it is enough that we can find 4 points that can be shattered. It is not necessary that we will be able to shatter any 4 points in 2 dimension. For example, 4 point placed on a line cannot be shattered, which is true. If 4 points shattered on a line, then it cannot be done using a rectangle, okay? I mean shatter any 4 points. Any 4 points is not possible. Any 4 point is not possible. Here this rectangle, see, this rectangle is shattering these two, you know points, and so these 2 points comes under one region, and this point comes in the another region. Okay, so another thing, you can see this rectangle has shatters these 2 points, this one and this one, and these 2 points left out, so it's a kind of shattering. So again, if you see this one, this longest one, this has shatters these 2 points. Which 2 points? Let me make it black so that it will be interesting for you. Let's say color is black. So in this case, this point and this point has been shattered by this rectangle, sorry, this one, right, this one. And then there are many, so and then this rectangle has shatters. Okay, let me rub it so that you'll understand in a better way. Okay, so this rectangle has shatters these 2 points. So this point has come, these 2 points has come in, have come in one region. This is one region, and this is outside another regions where this 2 point comes. So this is possible. However, we cannot place 5 points in 2 dimensions. This is possible. This is possible only for this 4 points. So it is not necessary that we will be able to shatter any 4 points in 2 dimensions. That is also a case. For example, 4 point placed on a line cannot be shattered by a rectangle. However, we cannot place 5 points in 2 dimensions anywhere such that rectangle can separate. So if I increase another point, 4 to 5, then it will be difficult by a rectangle to shatter this 5 points. It's not possible. If it is 4 points, 2 points can be taken out, and positive example and negative example will be shattered by rectangle. But if the number of points increase to 5, it will be not possible. Okay, so VC dimension of a classification model. So this material I have taken from Wikipedia. So a binary classification model F with some parameter vector theta is said to shatter a set of data points x1, x2 up to xn. So if for all assignments of label to those points where there exists theta such that model F makes no error when evaluating the set of data points. So whatever you have discussed, that is only the case. Okay, so parameter vector binary classification model F. So let us say this was our classification model where this F is shattering these two points from the negative. Let's say these are negative points. This is also negative. This is also negative. So this, let's say these are positive points. These are positive points. So it's shattering. Okay, these two can be taken out. So that is what parameter vector theta is said to shatter a set of data points if for all assignments are labeled to those points there exists a theta such that model F makes no errors when evaluating the set of data points. The VC dimension of a model F is the maximum number of points. VC dimension of a model F is the maximum number of points that can be arranged so that F shatters them. More formally, it is the maximum cardinal D such that some data point set of coordinate D can be shattered by X. Now, if F is a straight line, let's say F is a straight line, the model F is a straight line as classification model. Okay, classification model F can be straight line, it can be a circle, it can be any graph, okay, any polynomial, okay, any curve. But here, let's say the F here in this case we have taken rectangle. So this is the function, rectangle function you have taken. Here let's say the function is a straight line, and let's say if straight line can do the classification model points of two-dimensional plane, and plane is also two-dimensional, that also you have to remember. That is the model used by a perceptron. The line should separate positive data points from the negative data points. There exist 3 points that indeed be shattered. So the straight line can actually shatters maximum 3 points. Okay, it can shatter maximum 3 points. Any any 3 points that are not collinear can be shattered. If the points are collinear, even though they are positive, it cannot be shattered. If 3 points, positive or negative, whatever may be the combination, if they are not collinear, then the straight line can shatter them. Okay, so this is the message. So however, no set of 4 points can be shattered. Okay, and that has been represented by Randon's theorem. Any 4 points can be partitioned into two subsets with interesting convex hull. So it is not possible to separate one of these two subsets from each other. Thus, VC dimension of this particular classifier is 3. So if somebody asks, so here you can see that this is the blue one, and this is the red one, this is the red one, this is the straight line. This is blue, or navy blue, whatever you say, and this is red. So this is the straight line. So it has shattered these 2 points. In this case, all three are negative. It has shatters. In this case, also positive, negative, negative. So this is 4 points. You see, 1, 2, 3, 4. So one straight line is not sufficient, right? One straight line is not sufficient. We need two straight line to, classify them or shatters them. So here in this case, you can say the rectangle is actually shattering 4 points. Okay, here straight line is shattering 3 points, although, but those points has to be non-linear. It shouldn't be collinear. Okay, so that are not collinear. It should not be collinear. So this is, so Vapnik dimension for straight line is 3. Vapnik dimension for straight line is 3. Okay, that is maximum 3 points it can shatter, right? And thus the Vapnik dimension, VC dimension of this particular classifier, the straight line, is 3. It is important to remember that while one can choose any arrangement of points, that arrangements of those points cannot change when attempting to shatter for some level assignment. Note that only 3 of the 23 2 to the power, this is 2 to the power 3, only 3 of the 2 to the power 3, 2 to the power 3, which is nothing but equal to 8. So you can write it 2 to the power 3 equal to 8 possible level assignment. So if 3 points are there, we have 8 possible ways leveling is possible. Okay, and as shown on the 3 points. So you can level here 8 possible way, positive, negative. So here you see this is one of the way. Let us say this is 0, this is 0, this is one way of leveling, this is 1, this is 1, this is 0 way of leveling, this is 0, 0, 0. Okay, there this is 1, 2, 3, and there are many 5 other ways to level them. If we have 3 points, wherever we have 4 points, the concept will be different. One straight line is not enough, so we need maybe a rectangle to shatter the points. Okay, now what is the use of this Vapnik VC dimension? In statistical learning, the VC dimension can predict a probabilistic upper bound on the test error of a classification model. Vapnik proved that the probability of the test error distancing from an upper bound is given by this. Okay, so test error is less than training error plus less than equal to training error plus this component, where D is the VC dimension of the classification model. Okay, this D, this is the VC dimension of the classification model, and this eta is in between, this eta is in between 0 to 1, and n is the size of the training set, obviously number of instances. Okay, and this formula is valid when n is very large than D. Okay, so D has to be very large than the Vapnik dimension, right? VC dimension. N has to be very large, very, very large. When D is larger, the test error may be much higher than the training error. So if D is larger, means test error will increase further, right? So the D has to be very, very small than number of points that we are considering. This is due to overfitting. Okay, that occurrence will happen when the when the d is large, the test error will increase, and that will be happening, the overfitting will happen. Okay, so the VC dimension also appears in sample complexity bounds. A space of boundary function with VC dimension d can be learned with this samples n equal to this many number of samples, where epsilon is the learning error and delta is the failure probability. Thus, sample complexity is a linear function of VC dimension of the hypothesis space. In computational geometry also there is a use. In computational geometry also there is a use. So VC dimension is one of the critical parameter in the size of epsilon nets, which determine the complexity of approximation algorithm based on them. Okay, a range sets without finite VC dimension may not have finite epsilon net at all. So these are two solid use of Vapnik dimension.